for the your mic is muted. So could you unmute your mic?
Yes, sir.
Okay.
Yes,
Yeah.
I'm ready.
So are you ready?
Yes.
Is it okay? Let me see. Well, let's begin. Hi everyone. Now let's start the Friday session. The first speaker is Kantaro Ohmori. He will give the last lecture of topological aspect of symmetry in row dimensions. Please start.
Thank you. Thanks. So first, I again do the recap of the last day session. Okay, so yesterday I talked about the two topics. One was the group cohomology, and the other is the SPT. So here the group cohomology, I talked about the second cohomology for the group, and like this one is like we had the derivatives that sends two cochain to three cochain, where two cochain is just a function of the two elements of group valued in U1, and like this and yeah, and so this the cohomology is defined like in the usual sense. Okay, and this classifies the projective phase, okay, of a symmetry in quantum mechanics. Okay, so that was one story. Another story was about the SPT. So in that section, I talked about a much larger picture. So generally, if you have some anomalous system, in D+1 dimensions, then the hypothesis that the researchers in this area generally assumes, but not proven, I think, but what is not proven is that, or even formulated, I would say, is that it's actually a boundary of some SPT, the symmetry-protected topological phase, in D+1 dimensions. And yeah, rather we usually use this as a definition rather, and there should be more intrinsic definition of anomaly of a symmetry on purely in terms of D+1 dimensional theory, but often we use this as a definition. So this hypothesis is actually not even formulated, but that's the theme we often use, and I explain what the SPT is. SPT is some whose ground state is something you can make the local unitary to make it tensor product states, something close to the tensor product states, but you cannot do that operation with respecting the symmetry. Okay, that's as a definition of SPT, and I also saw the example of SPT for the SO3 case. So that's this. Okay, so I talked about this state. Just that each side consists of 2 qubits, the bipartite system, and the state have this kind of entanglement structure. So this green line shows the EPR pair or Bell state, and what's peculiar about this is that if you cut the chain somewhere here, say, then there's a isolated qubit. So on the boundary, you get the boundary. There's a limit. There appears 1 qubit worth degrees of freedom. Okay, so that's the one explicit manifestation of this hypothesis. Okay, so any question? Or I mean, yeah, both for this recap or more general other parts of the yesterday's lecture. Yeah, I want to do the correction that I use the SI, this state, I call it SI. I wrote that this up down this like singlet, but it's more precise to just use the Bell state. This is the more consistent one. So I revised the lecture note. Yeah, I also revised the some equations in that I didn't explicitly talked about in yesterday's, but related part anyway. Yeah, so that's a correction. Okay, so yeah, so this state is more like just a most simple Bell state. Okay. Okay. So if there is no question, then today, so I spent first 3 days for just the quantum mechanics, and so I should say something about the 1+1 dimension. I mean QFT. Okay, so let me talk about this example of the 1+1 dimensional or 2-dimensional periodic scalar theory. That if you have ever read studied the string theory, this is very familiar thing. And so this, for the lecture note, I'm skipping section 3.1 and 3.2, and I'm jumping in on to section 3.3. Okay, so this system have a U1 squared symmetry, namely the momentum and the winding, as we will see, symmetries, and this U1 squared symmetry acts on the Hilbert space quantized on a circle nicely. There's no projective phase. It just nicely acts on them. Okay, but however, it's very well known that this U1 squared symmetry have an anomaly that traditional sense, the perturbative anomaly, and but so to match with this theme of this lecture, I'd like to see it as some kind of projective phase to emphasize that it is actually the generalization of the Wigner's projective phase, for the quantum mechanics. And to see the projective phase, actually, we have to think quantize the theory on an interval with boundary. Yeah, so you can pick a boundary condition for each of the boundaries of the interval, and if you carefully think about the action of the symmetry on this Hilbert spaces on the intervals, then there's a projective phase, and that projective phase is going to be that, yeah, generally classified by H3 object. That's the today's story that I want to deliver. Any question?
So here you consider the spatial interval between the 0 and 1.
Well, the length is not important.
Yeah, but is it okay to consider like a half, like a what is it, open interval, like a 0 to infinity?
Oh yeah, you can do that. But for that case, I mean, you want to, well, yeah, you want to do the, I mean, I want to think about the Hilbert space, and the Hilbert space on the non-compact space is a bit scary. So
Okay.
you want to do the IR infrared regularization that effectively just put the boundary on the other side.
Okay.
Yeah. So. Okay. So 1 + 1D periodic scale theory. Okay, so I use Polchinski's notation. So Polchinski's book, volume 1. Okay. So I have scalar x, just a single periodic scalar, depending on the coordinates and the spatial and time coordinates of this two-dimensional QFT. And so this is scalar, and I identify x and x plus 2 pi r. So this is periodic scalar. The action, the Minkowski action, is the standard one. Okay. So this is action.
And can you have potential? Like you only consider the massless?
So here I only consider massless scalar. You can though, like, well, so yeah, okay, just yeah, you can potentially have cosine or like a deformation. Yes. So here, what I do is that I demonstrate that there is a projective phase without turning on the cosine deformation, that because it's easy. Then but once you find some anomaly, then as long as that the symmetry is preserved, then the same projective phase should persist. So that's the same story as I did for the quantum mechanics. So here I'm taking this is massless. Free. So it's easy to solve. Yeah, and yeah. I think I shouldn't assume that every student have read the Polchinski nowadays. So I'm doing the lightning review. Okay, so the equation motion is usual Klein-Gordon one with massless scale, massless Klein-Gordon. Okay, and momentum is this. Now the Hamiltonian is the usual one. So far so good. And what do you do? So then first let us quantize on a circle. Okay, that's the only connected closed manifold on one dimensions. So only choice. And okay, so what to do? So we do we take a general solution to this equation of motion, and okay, so and then we put the canonical canonical commutation relation. That's the between x and pi. Okay, so that then we construct a Hilbert space. So that's the usual canonical quantization of the QFT. Okay, so the solution to
when you say S1, is it when you say S1, is it like interval? You impose a periodic boundary condition on the interval, or
yes, yeah. So here, I mean, sigma is not positive, right?
like okay. I see here you don't consider like some other like a declared boundary condition and so on. Only consider the periodic one.
I will do Dirichlet later.
Ah,
So, yes. First I do on the periodic boundary condition, and to see the U1 square symmetry, and also to see that there is no projective phase in this case. Okay. Then I will move on to the Dirichlet. That's more, which is more interesting.
Okay.
Thanks for the question. Okay, so the solution to EOM is x sigma tau is some small x plus r w sigma plus 2 pi alpha prime p tau plus I alpha prime over 2 and here alpha m what to say, so e to the minus I u maybe u plus and e tilde m maybe I put the plus, so consistent, u minus where where so this is the general solution where this first, okay, this is some constant term, fine. This one, something proportional to sigma, and that doesn't, that's okay for this second order differential equation. If you sigma square, if you take the second derivative of sigma 0, so it's okay to have it. However, this W is quantized, okay? Because if you go sigma to sigma plus 2 pi, this gets the 2 pi WR, okay? And we also have this periodic condition in X. Okay, so if you go around the circle once, then X might go around on the target S1, but by the integer number of times. Okay, so that's the winding. So this is called the winding number. Okay. Then, well, this U plus minus are the light cone coordinates. So I put the tau plus minus. Okay. Then, so the canonical commutation relations are for this X and P, you have usual commutation relation. Okay, so this is the center of mass. So this is center of mass of the string, and then you have these oscillation modes. Okay, so this is the scalar field theory. Okay, so what to do? So here in the general solution to E or M, we have some integer, right? That's so the XP and alpha tilde is before consideration just a continuous some real numbers, but this W is quantized. It should be valued in Z. And what to do in such cases is that for each W, we prepare some Fock space generated by these operators. I mean some Hilbert. For each W, we prepare the Hilbert space, and then the total Hilbert space is just a tensor. So direct sum of W. There's a typo in the lecture note. It should be direct sum over W. So, okay. So And also, okay, also for this part, this is a usual commutation relation, well, where the h bar equals 1. But I put the x is periodic. So x is x tested by r. And as we did in the quantum mechanics case, in such case, this momentum is, so then this, it means that momentum is quantized. Okay. Because the wave function has to be periodic in x. So that means that the momentum is quantized. And so P of RP. So RP is, am I right? P of RP is an integer. Goes to n and is should have been 2 pi e to the I x over r. So and this is P. I'm confused. So P is, yeah. So this is integer. Okay. So a general state looks like, so general state looks like as follows. NW. So we are this NW of the state such that the fixed momentum winding number, momentum and winding number and also I demand that this state is a vacuum with respect to these oscillators. So this is the algebra of annihilation, creation annihilation operators. And I call the alpha and alpha tildes with positive m. Here this m and also positive m. Sorry for the n is duplicated. But anyway, yeah. So for positive alpha and alpha tilde with the positive number, the label to be the annihilation operator and the negative number to be the creation operator. Okay, so I demand that this state have eigenstate under P and also winding having some fixed winding number, and then this also, which is a vacuum with respect to these oscillators, the infinite set of oscillators. So we have plus I and W equals to 0. J with IJ so here minus IA JB negative. Sorry, also positive. Okay, so far I'm just saying that first for each n and w we prepare the Fock vacuum, and then the total Hilbert space is spanned by this acting the oscillation, okay, oscillation mode by acting the creation. Okay. Okay. So the state with this action of created by this action of alpha and alpha tilde is some very oscillating string. Okay, but these alphas are not important in our story, so I do not talk more about this. Okay. And then the Hilbert and the Hamiltonian, which is not very important, but Hamiltonian is this in this in terms of these operators, you can write down. Here's also typo. Sorry, it has to be n, and I shouldn't use n here. So I don't know, m. Okay. Let me memo. This is this typo. Lecture note. So typo in 3.10. There has to be m here. And this is okay. Any question? Please ask question. I'm doing in the lightning speed. Okay. Well, if there's nothing, then I proceed. So and there's always two quantum numbers, which is obviously preserved by this Hamiltonian. That n and w. So both are integers. So we have u1 squared symmetry, and the charges whose charges are n and m. Okay. So explicitly we have unitaries that u of p of lambda and u of w of lambda. So these u1s are called the momentum u1 and winding u1. So this one is momentum u1. Momentum u1. The latter one is the winding u1. And the explicit action and also the lambda is a parameter. Lambda in R over 2 by Z is a parameter. And the explicit action is just U lambda P and W is usual action. U winding of lambda acting on W is e to the I lambda W and W. Okay, and these operators commute with the alphas, so the oscillation doesn't do nothing. It just the momentum and the winding. Okay, so these are two symmetries, and this action is very simple. There's nothing subtle, like no projective phase. Okay, in periodic boundary condition, that e to the, so that's like 2 pi rotation. Both of 2 pi rotations are identities. And also the two commutes. There's okay. So you see nothing wrong or subtle on the periodic boundary, with periodic boundary condition. We about this U1 square symmetry. Any question? Okay, so then let us move on to the case with the D-shaped boundary conditions. Okay. So here we take the sigma is inside 0 and say maybe L, or maybe let me just go with the 2 pi. Okay, that doesn't really matter. And okay, so the length doesn't matter anyway. So yeah, and so there are two boundaries at the sigma equals to 0 and the sigma equals to 2 pi, and we put the D-shaped boundary condition. D of theta L and D of theta R defined by the D. So we demand that sigma at sigma equals to 0, it's R theta L, and at the sigma equals to 2 pi, it's R theta R. Okay. Okay, so we put the generally different boundary conditions. We have to do this. And so in the picture, so this is the x direction, and this is sigma direction. and we have 0 and 2 pi. Okay, and okay, and here is theta r theta L r theta L, and like the string switches like this. Okay, so with this boundary condition, the solution to EOM looks like this. So now the center of mass cannot completely freely move because the two boundaries are fixed. So now we don't have a constant piece. Let's say the constant piece is fixed to this value. Then we have this, and there's no tau prime as a tau independent. Linear term, then this one, sine m sigma over 2. Okay. It has to be sine because yeah, the two ends are fixed. And then so with this ansatz, this boundary condition is automatically satisfied. To satisfy this right Dirichlet boundary condition, the W with this parameterization, the W has to be in sigma r minus sigma L over 2 pi plus T. Okay. I mean, this means that W has to be this number plus some integer. Okay, so it can be, so X is 2 pi r periodic. Okay, so it might be like so there's a periodicity. So here is r theta r plus 2 pi, and this string is also fine. And the W is with this parameterization, the W is this, or this. Okay. So W has to have some fixed offset, precisely theta r minus theta L. Sorry, this is W 2 pi r W to be precise. 2 pi r W. Okay, so the W still have the freedom of integers. Okay, but the W itself is not an integer. With theta L and theta R are not equal. Is this clear? Okay. And okay, so then yeah, the rest of the talk, this oscillation mode doesn't matter, so I'm going to ignore it. Okay. Then so let's study the U1 squared action. U1, so U1 squared actually. And so first notice that that this one breaks the momentum U1. So they call that the momentum U1 is something generated by the momentum. I mean, canonical momentum for the center of mass of the string. Therefore, it moves the string. And if it moves string, translate the string, then the endpoint value moves. Okay, so it's broken by this boundary condition. Nevertheless, so U1P momentum breaks, is broken by this way. But we do not abandon this symmetry, and rather we think that U1 P sends a particular Dirichlet boundary condition to another boundary condition. So maybe I UP lambda, shift by lambda, because it moves the string, translate the string. Okay.
Here there is two zeta. You
yes.
You translate both of them at the same time.
Yes. So okay. So let us denote that the H, that curly H of theta L theta R is the Hilbert space interval 0 to pi with the boundary conditions d theta L and d theta R. Okay, so then this thing is a linear map from one Hilbert space to another Hilbert space. Okay. And okay, so and I suppress the oscillations. I only write the winding, so some state winding in state with fixed winding. Okay, by this. Okay, so then I have a map like this. Okay, and this commute with Hamiltonian in the sense that the two have, so the two have the same energy. Okay, so that's just like, yeah, the Hamiltonian is the same. You just this one and you just ignore this word. So yeah, and do something here, but yeah, so yeah. And also it's obvious that the same W satisfies this condition on both sides here and there, because the difference between theta and theta L is the same. Each cell and cell are different, but the difference is the same because it's just a translation. Okay, all intuitive. Okay, then so that's your momentum. Then your winding. So winding is preserved, and naively let me move this to the next page. So naively, this winding U1 so this doesn't change the Hilbert space. And since WL to just extend what we saw in the S1 case, and then we might write like this. W L. Okay, but let me call this U tilde. Okay, so this one, but this one as projective phase. Because so when lambda is 2 pi, okay. So when lambda is 2 pi, this one is I theta R minus theta L identity. Okay. It's projective phase. It's just an overall phase on the fixed Hilbert space. I mean projective phase on the fixed theta L theta R. Okay. Okay, and this is please recall that this is because that this W is not an integer, but the integer plus some fractional number or like the remainder. Okay, so this one breaks the periodicity. Okay, so remedy this by defining so for the remedy is just we define U W sub lambda equals to U tilde this action times e to the I lambda of let me see theta L minus theta R over 2 pi, where this square bracket I define is a number between 0 and 2 pi and theta is equal to 0 more 2 pi. Yeah. Let me explicit that to this is going to be important. So here this looks trivial, but this square bracket emphasizes that we take this particular fundamental domain, okay, between 0 and 2 pi. And okay, so then this one resolves, and yeah, and also this is not theta L minus theta R. Okay, and this is actually important. And we take this square bracket for the each left and right separately, and not to the difference. And this is motivated by the locality that I don't have time to emphasize. That we want to do something for each of the boundaries, not the pair of the boundaries, but we want to define some operation. This, I mean, this is something. This is the phases defined for each of boundaries. Okay, you can define this square bracket of theta and theta R separately without referring to the other boundary condition. Okay, if you want to do this, then you have to know what theta R is. Okay, so that's the difference of this and this, and choosing this is important. We stick something to something that defined for each of the boundaries, not to the pair of the boundaries. Okay. Okay, so then this one is good. This one is good. This one is so just single winding U1 winding is not anomalous in this. You can remedy the action by in this way, in the local way. However, if you consider both of this and that, and you think carefully, you have to be careful about this take fundamental domain, then okay, then you have this. So consider the composition of the commutation between the U of winding U1 and momentum U1 acting on intervals. And here so this is U lambda PP acts on H theta L theta R. Okay. Then this one, because this, so I assume that this operator acts on this, but then this U lambda PP shifts these thetas. Okay, so this one acts on H of theta L plus lambda P theta R plus lambda P. Okay. And equals to, so this is proportional to this acting on the same theta L theta R. Okay, so the domain and the codomain matches, and also the two are proportional to each other. but there's a proportional constant, and that's lambda w of lambda plus theta L minus lambda plus theta, where this curly bracket of theta is theta minus square bracket of theta. Yes. So here we take that theta and L and theta R is between 0 and 2 pi. Then this phase is non-trivial when exactly one of the theta L plus theta, lambda, this is lambda p plus theta L or lambda p of theta R exceeds 2 pi. So that's like the original this is 0 string is like this, and then we translate by lambda p, so it might become like this. But then if you use the definition of winding number by this, that w shifted by this quantity, then winding, so this lambda p shift actually changes the winding. So this counts the winding. Okay, so that's why there's a projective phase.
In the change of winding means winding number, it does not mean the winding number is changed, but
well, that's definition of winding. So the definition of winding number using this operator is that whether it crosses the 2 pi,
okay,
the number it crosses the 2 pi or 0, and that's the definition of winding with this definition. But
so the new definition of the UW without tilde is that one, but the U tilde is the original one. So that
So with tilde, then the winding is the difference between the here, and that's not changed. I mean, to be precise, with tilde you define winding by integrating along the string. So that is not changed, but the problem for that choice is that it's not 2 pi periodic. So you have to choose, Fitch property, and the point is that you can you have to abandon either of the commutation with the momentum or the 2 pi periodicity, and you have to choose one of them. You cannot achieve both. Okay, so this is the projective phase. So yeah, this is the okay, and it's very well known that U1 squared in this model has anomaly, and if you open up Polchinski, he explains in a completely different way of as a 2-point function of current. Okay, but here we've seen the same phenomena as some projective phase of the actions on the Hilbert spaces with boundary conditions. Okay. And I personally do not know how to, smoothly connect the two definitions. So please think about it if you want and teach me about it. But I strongly believe that the two things are, of course, the same thing. Okay. And one advantage of this way of seeing the anomaly is that it's straightforward to say focus on the subgroups, for example, of U1, the discrete subgroup, and you just restrict your lambdas to the subgroup. Okay, so Z2 diagonal Z2 subgroup is also anomalous. So if I define U of Z2 to be UW pi U P pi, okay. So this is pi rotation for the both directions. So it's Z2, but there's a projective phase I minus pi plus theta R plus pi plus theta L over 2 and identity. So yeah, that's the one. Okay, and these projective phases cannot be removed by redefining U acting on theta L, theta R boundary conditions to, like, you might want to modify this. Let me generally called some G is some element, the group. Okay, you modify this, but you want the modification is local. So local modification. Modifications, which I define by this beta of G theta L beta G theta R.
Hello.
Hello?
Yes. Could you demonstrate why that anomaly piece, this why the phase you wrote, and the last line
This
is
one?
not, yeah, right. When it is not the same as the theta left minus theta right.
So with this, yeah, so this one, let me go. So this is pi shift, like when this is non-zero, when like theta R is between 0 and pi, and theta L is pi and less than 2 pi, or vice versa. Like theta R is pi less than 2 pi, and because so for this case, this is 0. This one is pi plus, by def, the pi plus theta is in between 0 and 2 pi, and this curly bracket is defined by this, and square bracket is defined by this. So this is basically it's is 0 when theta is less than 2 pi, and 1 when theta maybe 2 pi. What is my definition? What's my definition? It's a 2 pi. I'm always confused. It's 2 pi. So 2 pi. It's theta is exceeds 2 pi. That doesn't exist. Okay. So here, in this case, that the pi plus theta is less than 2 pi. So this one is 0, but this one, pi plus theta L, exceeds 2 pi. So we get the 2 pi, and we have half here. So there's a sign. And this is the same. I mean, non-trivial one. Non-trivial. Okay. It's some peculiar discrete function.
So can you describe it pictorially in your figure there?
Yeah. So this is when so here particularly this is a pi shift, and then like so this figure is like the situation here rather. So let's say that this here is a pi. Okay. Then so if you do the pi shift, the theta R exceeds 2 pi, and then there's a non-zero contribution for this, but then theta L is below pi, so you don't get contribution from here, and therefore you get the sign. Then by the definition of winding in terms of this u w lambda, yeah, pi shift changes the winding by 1. Yeah, so yes, of course I'm looking at very subtle effect.
Right. So far, I guess that the question is why such a subtle effect can pick up some topological effect?
Well, I mean, I'm claiming this is the topological effect, one manifestation of topological effect, and yeah.
So topology over which space?
Nice question. That I don't know really, but yeah. Well, it's topology of the classifying space of Z2. It's very obscure.
Let's go.
Yes. Yeah. I don't have a good answer. This is. Yeah. I mean, I can introduce the tons about algebraic topology to make it looks like some topological mathematics, but I rather wanted to be like a physics and like poking some subtle face. That was my choice. Then yeah. So what in what sense this is non-trivial, and this is non-trivial phase because in the sense that you cannot remove this by this modification, and note that modification, I also demand the modification depends in the left and right boundaries independently. Okay, if I allow to modify by this factor, then everything is gone, obviously. But sorry, I said something wrong. No, you can do this, but then you're losing the periodicity for the other part. Yeah, so yeah, this and that. So yeah, so you have to demand, yeah, we have to demand that the local modification to be local modification like this. Okay, so this phase itself can be removed, that you demand beta is this, you can remove, but then the problem appears when this U Z2 acts on the theta L, different theta L. So you can uniformly remove everything, I believe. Yeah, so that's the am I right? Yeah. That's the thing. And yes. And so I don't have time. So this defines. Okay. So generally, so for some group G and some boundary condition B, then if you define three cochain alpha G1, G2, G3 by the projective phase G1, UG2 acting on G3 acts on this boundary condition, and boundary equals to U G1, G2 on G3 B and what? And yeah, so this one is, I define the three cochain by this way, and well, I skip the detail, but then some locality assumption. We can show that delta 4 of alpha is 0 by associativity. Of use, where delta 4 I define this. So this is the fourth derivative. And the projective phase is classified by what? By H3G. This is a third homage group. And yeah, I think it should be possible to generalize this story to higher dimensions, and in higher dimensions it should be like boundary condition, and you have a disk and put the boundary condition on the left of different boundary condition for the left of the disk and right of the disk, and blah blah blah. You have to do something like that. But yeah, you have to put more boundary conditions, I think. Yeah. Anyway, that's the thing. And I've been emphasizing the relationship between the anomaly and the boundary condition. And actually, there's a important theorem recently proven by Songren and Wan. Let me state this. And that is that if there is a boundary condition B such that it is preserved by a symmetry. So G B equals to B by group G. So G is of course a symmetry of the theory. Then G is non-anomalous. So this is important. This is a recent result in 21. But having said by other persons for years, but they formalized. And yeah, so again, if there is a boundary condition that is preserved by a symmetry, the symmetry is non-anomalous. In other words, if the symmetry it has anomaly, then there is no symmetry preserving boundary condition in the theory. Okay, so I think that's important consequence that I mean, this is one. Yeah, I mean, there's one belief mainly held by mathematicians that the QFT, if you know everything about the boundary conditions, then the bulk of the QFT is reconstructable. That's called the Corbolism Hypothesis, and this is one rough statement associated, I mean, to that the boundary condition should at least know about the anomaly of the symmetry. So this is important.
So is it possible to understand your statement in your previous example?
Yes.
By saying that,
so
I mean, the both U1
yeah,
is
I mean,
the position of a boundary, so this is anomalous.
Yeah. When yeah, so I think something I wrote something in the introduction note. Let me try to quickly say something. Well, so the point is that this cohomology class. So point is that the cohomology class is the property of the theory. is a property of theory, not the boundary condition. Okay, so for any choice of boundary condition, you should the projective phase should be cohomologically the same. Okay, this is because that the B1, B2 are boundary conditions. Then there has to be a boundary condition like the sum of the two, and such that the H of this one is HB1 B3 plus HB2 B3. It's like you have a qubit that's switching the boundary condition. This is like a qubit on boundary switching. Boundary conditions. And then UG acts on this direct sum in a nice way as a projective representation. And so the projective phase has to be uniform. So projective phase has to be uniform on this direct sum space. And for that to be true, the projective phase restricted to each of the subspaces are the same. Okay, so for a single theory, every boundary condition should share the same boundary condition. Okay, so to calculate it, you can pick one bound. To calculate the anomaly, you pick one arbitrary boundary condition you like.
But here you are saying that within the Dirichlet boundary condition, for example, if you change one boundary condition to the Neumann boundary condition.
Well, so we believe, I think at least axiomatize. I mean, if I axiomatize the QFT, then I also demand that that's also possible, that the Dirichlet and the sum of the Dirichlet and Neumann boundary condition should be the same, and that it's more. I agree that it's more non-trivial statement, but yeah. I mean, another way of stating it is that you can also modify the boundary by deform the boundary condition, okay, by turning on some boundary operators, and that can turn the Dirichlet boundary condition to Neumann by deforming and RG flow, and this process shouldn't destroy the symmetries. Yeah, I mean it can break the symmetry on the boundary, but then this broken symmetry becomes like the map from one Hilbert space to the another, and in that sense it's also still preserved in the bulk. And then you can show that the projective phase should be the same. Yeah.
I guess in your example, the boundary condition is such that you fix, I guess, two D-brane position, right?
Yeah, yeah.
And when you say boundary condition independent, do you mean that theory with the D-branes and the theory without D-branes are the same?
Yeah, so you can do this whole exercise with say Neumann boundary condition. Okay, instead of Dirichlet. But the Neumann with that the partial x takes different values from left and right. So that's say TDR of this whole picture. And then I mean, for the Neumann boundary condition, this momentum U1 is preserved, winding U1 is broken. So the intermediate calculation looks different, of course symmetric because of the TGRT, but different. The intermediate calculation will be different, but you should get the same cohomologically same projective phase. That's what I'm saying.
So this anomaly structure is a somewhat invariant under TDR transformation.
Well, in this particular case, well, it's not really the TDRT is not the reason, but in this case, yes. Yeah. Yeah.
So then, what kind of the structure is this? The quantities measuring and pictorial. If it doesn't care whether this is the dimensionality of a D-brane and so on, or presence or without presence of the D-brane, what does it counting?
So
what kind of what do we mean by the topology?
So in this context, when I say topological, it's like that it cannot be, well, basically depends on the discreteness of this cohomology that I didn't explain, but this is discrete, and so it's topological in the sense that it's not deformable with some continuous deformation, both of the boundary and bulk, as long as the symmetry is preserved. That's the meaning of topology here. And yeah. Yes. Yeah, I mean, yeah. Well, abstractly, I'm talking about some topology of bundles of QFTs of some huge space, but I don't want to introduce those kind of terminologies. Yeah.
Hi.
Yes.
Okay. I know that Yuji Takikawa and Changzhe wrote one paper to introduce that U1 gauge theory can also have a EM duality anomaly.
Yes, yes.
Could we use the theorem to understand anomaly from boundary condition?
Believe so, but I don't know how to what they do explicitly. So
yeah, but because you can also have the boundary condition, but I expect that the boundary condition is also EM duality invariance. So in this sense, it's not an anomaly, but we know that it's an anomaly.
Well, it's not clear that for me, at least, that there is a EM invariant boundary condition for the Maxwell theory.
Okay, because we can also, when we do the apply EM duality to the U1 theory, and then we can always do the redefinition for the background field. So it's why what I say the EM duality invariance.
Yeah, but the boundary condition. I mean, if you want to apply the Songren-1 theorem, I believe that you were talking about, then
yes.
Yeah. So then, so the question is whether there is a boundary condition that is unchanged by EM duality.
So how do you say unchanged if I have the same form? It is invariant.
Whether that symmetry can act on the Hilbert space without doing it without or well more intuitively like here this is, I mean, the EM duality is like T duality is very analogous to T duality of the periodic scalar. And here, the boundary condition I'm picking, that which is the issue, does not preserve this T duality because the T duality sends the issue to Neumann or changes the winding and momentum. So in that sense, it's not like that. And so the question, the question is that in this case, whether there is a boundary condition that is like some half of Dirichlet and Neumann, and that can be unchanged. So that's
And first of all, this is the end of the lecture, right?
yes. So yeah.
Yeah, let's thank the speaker again for the very nice talk.
Thanks for the listening. Yeah.
And there is a question in the chat.
Okay. I'm ready.
So Professor Kim asked, how can I understand this via gauging both momentum and the winding?
So you cannot gauge both momentum and winding or the diagonal of winding because it's anomalous. And so the point is that you cannot find
so what I'm suspecting is if I turn on some background gauge field, both momentum and winding, then I'm suspecting some mixed anomaly term.
Yes.
What I do not understand is what is the role of boundary condition here for that kind of thing. That part I did not understand.
Yeah. So yeah, more traditionally, of course, we say that with the background, the gauge invariance is broken. Here. Yeah, in a sense that the putting different boundary conditions is like putting background is a way to put a background in. So that's one answer. I mean it's like a flat. Put a flat background on top of the boundary to change this like momentum background, momentum U1 background on the boundary to change this the Dirichlet boundary condition. So this is a way to probe the background dependence of the position function secretly. So that's one answer. Yeah. Yes. And also in terms of the Songren 1 theorem, that if the symmetry is anomalous, then there is no boundary condition that is preserved by this symmetry. And if you force to gauge it, then you lose any boundary condition, which is actually still fine it might just mean that pure gravity anomaly, but it looks like something, but yeah, one way of saying it.
And is there other questions?
May I ask a question?
Please.
So yeah, first of all, thank you very much for this. Very nice lectures, and that were very enjoyable. I really enjoyed it. I have a question about this classification by third cohomology of group. So, naively speaking, this third cohomology is going to classify the violation of associativity, right?
Yes.
So, but here, in the equation appearing here, this is, so this alpha, plays the same role, I think, as the,
Yes.
classification of the violation of the associativity. So by introducing the, boundary conditions. So this, is this operation possible for, any higher dimensions as well?
So in higher dimensions, you need to consider the higher, of course, higher order group cohomology. If that's the question, then yes, classification is by higher order. Like,
oh yeah.
Yes.
So if we consider even higher dimensions, then there's going to be something like the, so for example, the H4 is going to classify the violation of the associativity, something like that.
Yes. That's violation of pentagon identity. Yes. That's true. But here, I somehow dissent that. Usually you say that H3 characterizes the violation of associativity, and I dissent that, or like in a sense, the loop, that as the violation of associativity to the violation of multiplication law, but acting between this use, which is not yeah. So I secretly exchanged that violation of associativity to violation of the multiplication law, but by paying the price that let this U of G acts on is not the linear map from Hilbert space to itself, but to the different Hilbert space linear map between the different Hilbert spaces. So that's Here I'm secretly doing some that kind of thing.
So yeah, this operation looks very interesting, and so this is descending procedure is possible for higher dimensions as well, right?
I believe I haven't seen, I haven't done explicitly, but I believe that higher dimensions you need to think some disks, and with different regions of disks have different boundary conditions. Then you need to have a boundary condition changing operators, blah blah. But yeah, so that I believe.
Has there any reference? That is
no. Yeah, well, sorry for doing something original or for the lecturing, but I think this is a bit original. So I don't have any direct reference for this. Yeah, but I believe this is possible.
But yeah, I think this operation looks very interesting, and yeah. Thank you so much for your talk.
Thanks.
Is there any other question?
I have a question. So you explained an example that anomaly in two-dimensional QFT is cohomology.
Yeah.
And also, can we understand the usual Prof anomaly in four-dimensional or six-dimensional QFT as cohomology?
Yes, but there's a subtlety for continuous symmetry that I skipped over. Well, although I talked about U1. So actually this group cohomology is not enough for the continuous symmetry. But with a suitable generalization that to take the topology of the group into account, then yes, it's a kind of cohomology group. Yeah.
And for generalized symmetry such as higher symmetry or
that's also you can do that. Yes.
Thank you.
Yeah. To be precise, for the this story is for the bosonic theory actually. So the theory without fermion. Theory with fermion, the cohomology itself also has to change to take into account the spin structure of the theory, of the manifold. But still the classification of the anomaly is a kind of generalized cohomology theory always.
Thank you.
Well, almost always. Sorry.
Thank you very much.
Yeah. For that, please refer to the UG's note. I think that's very clear.
Okay, and thank you very much for the very clear and nice 4 lectures in the APCTP Winter School. Let's thank speaker again for.
Thank you for inviting me. This good opportunity. Yeah.
And yeah, so now it's the end of the Kantaro lecture, and please, if you have any further question, you can freely ask or to have a discussion with the speaker. But,
please, yes.
And,